In the hostile environment of a growing brain tumor, where oxygen and nutrients are scarce, cancer cells adapt aggressively, rewiring their metabolism to survive, expand, and evade therapy. One such adaptation is the strategic use of glycogen, the brain's local energy reserve. Though typically stored in astrocytes to support neuronal function during energy stress, glycogen in the context of brain tumors becomes something entirely different, a secret weapon for malignancy. Some tumor cells hoard glycogen to fuel rapid proliferation and resist hypoxia. This metabolic flexibility gives them an edge, but it may also present a critical vulnerability. Blocking glycogen access or breakdown is emerging as a potential strategy to starve tumors and impede their relentless growth. In normal brain physiology, glycogen plays a backup role. Astrocytes store it and mobilize it during short bursts of high energy demand, such as during intense neuronal firing or temporary drops in glucose supply. But cancer cells, particularly those in aggressive brain tumors like glioblastoma multiforme, GBM, can exploit the system. They increase glycogen synthesis during nutrient-rich phases and then break it down during stress, such as hypoxia or nutrient deprivation. This gives them a powerful on-demand energy source that helps buffer against fluctuating microenvironmental conditions. Under the microscope of metabolic oncology, this adaptation looks much like a military stockpile. Tumor cells accumulate glycogen when possible, then rapidly degrade it through glycogenolysis to fuel glycolysis, producing ADP and biosynthetic intermediates even when blood flow is compromised. In essence, they are building an internal emergency reserve, a trait that may correlate with resistance to therapy, especially radiation and chemotherapy, which both rely on pushing cancer cells into energetic crisis. Furthermore, glycogen accumulation in tumor cells isn't random. It's often driven by dysregulated signaling pathways such as PI3K/ACT/mTOR, which promote anabolic metabolism and cell survival. These same pathways are known to be hyperactive in many brain tumors, suggesting that glycogen metabolism is not just a byproduct of cancerous growth, but a deliberately hijacked mechanism. Studies have shown that some tumor cells express higher levels of glycogen synthase and glycogen phosphorylase, enzymes involved in both the buildup and breakdown of glycogen, highlighting a tightly regulated, tumor-specific glycogen cycle. This opens an opportunity. If tumor cells rely on glycogen for survival under stress, then disrupting their ability to access or metabolize it could leave them energetically vulnerable. Experimental models have demonstrated that inhibiting glycogen phosphorylase, thereby blocking glycogen breakdown, can impair tumor growth, increase oxidative stress within cancer cells, and enhance sensitivity to chemotherapeutic agents. This strategy essentially traps tumor cells with unusable energy stores, full tanks they cannot burn. However, there's a challenge in targeting this system precisely. Glycogen is essential in certain normal brain functions, particularly in astrocyte neuron energy support and during recovery from hypoxia or seizures. A broad attack on glycogen metabolism could disrupt healthy brain tissue, especially in regions already stressed by inflammation or edema. Therefore, therapeutic targeting must be selective, ideally focusing on tumor-specific isoforms of glycogen-related enzymes, or on downstream signaling pathways that regulate tumor glycogen dynamics without impairing normal cellular function. Additionally, tumor heterogeneity complicates the picture. Not all brain tumors, or even all cells within a single tumor, depend equally on glycogen. Some may rely more heavily on glutamine, fatty acid oxidation, or direct glucose uptake. Still, in the hypoxic, poorly perfused core of many tumors, glycogen may serve as a critical survival mechanism. In such cases, combination therapies that both block glycogen use and target other metabolic dependencies could prove most effective. In summary, glycogen plays a double role in the brain. It's a protective energy reserve in healthy cells and a subversive fuel source in malignant ones. Cancerous brain cells that manipulate glycogen for their survival and proliferation reveal both a strength and a weakness. By targeting their glycogen stores or the enzymes that control them, we may be able to selectively cut off one of their most vital lifelines. While this approach is still in the experimental phase, it represents a promising shift in thinking, where energy metabolism isn't just background biochemistry, but a battlefield where cancer may finally be made to starve.